This course will cover the fundamentals of fuel gauge. Research shows that in daily life, battery issues are very high in the minds of consumers, in terms of anxiety about the availability of battery when they need it, as well as other issues, like safety and reliability. By providing a trustworthy fuel gauge solution, we can help the customer relieve this anxiety and enable them to maximize use of their devices. Accurate fuel gauges are integral to good battery management. They improve user experience, extend battery runtime. With the appropriate parts selection, customers can minimize solution size and increase safety and security. Historically, engineers could use simple voltage-based techniques on older chemistries like nickel metal hydride or lead acid to gauge batteries reasonably well. However, with the advent of lithium-ion chemistry, this became very challenging due to its peculiar voltage to state of charge relationship. For example, if the lithium battery voltage is 3.8 volts, the battery could be near empty, or 3/4 full, or half full. There are several reasons why using voltage alone for gauging lithium-ion batteries has been difficult. The plot on the left shows the voltage versus remaining battery capacity commonly stated in ampere hours at varying loads. The voltage curves show that there is more capacity available at light loads compared to heavy loads due to battery impedance. Also, the voltage curve is relatively flat in the middle section. The plot on the right shows how the voltage varies with temperature. At high temperature, more capacity is available compared to low temperatures. This is because the battery impedance increases as the temperature reduces. To address the problems with voltage-based techniques, engineers started using Coulomb counters to fuel gauge lithium-ion batteries. The idea was to measure how much charge, coulombs, is going into the battery, and also measure how much charge was coming out of the battery, and therefore estimate how much charge was still remaining inside the battery. While this technique was found to work well in short time frames, engineers found that over the long term, they saw unexpected high errors. The reason found was that the ADC measuring the current by looking at the voltage across the sense resistor had a small offset error. In the short term, this did not cause any problems. However, in the long term, this current, integrated over the long time frame to count coulombs, resulted in a drift error. This drift increased continuously with time. To correct these errors, the batteries needed to reach full and empty periodically. While reaching full was an acceptable requirement, reaching empty was quite problematic, as many applications stop well before the battery is fully exhausted. Maxim has invented various techniques to address both voltage-based as well as Coulomb counting-based fuel gauge problems. The customer has a choice of implementing these innovative fuel gauges on the system side or on the battery pack. These system block diagrams show two ways of implementing the fuel gauge function. This diagram shows a simple battery pack on the left side, connected to the host system on the right side. The battery pack contains the cell and the protector. The host system contains the application processor that communicates with the fuel gauge IC mounted on the host side, but connected to the battery terminals. The power management block on the host side contains the charger. This approach is suitable in several scenarios, such as the battery is embedded or not detachable from the host system. The battery is detachable, but the typical system life is similar to the battery life, around 2 years, at which point the entire system is replaced. This approach requires the host microcontroller to write the battery model to the fuel gauge IC at power-up. Since this approach eliminates the need for non-volatile memory inside the fuel gauge IC, it is suitable for cost-sensitive applications. The diagram at the bottom shows a smart battery pack on the left side connected to the host system on the right side. The battery pack now contains the fuel gauge, along with cell and the protector. The host system contains the application processor that communicates with the fuel gauge IC mounted on the pack side. This approach is suitable in several scenarios, such as the battery is removable. The typical system life is long, 5 to 10 years, and the detachable battery replaced every 2 years. In this approach, the fuel gauge IC contains the cell and battery information, as well as any learned information within itself, and therefore the host microcontroller simply needs to read the battery status. Since the fuel gauge IC is located in the battery pack, this approach also lends itself to further integration of other functions, such as authentication to prevent clones, and more sophisticated protection than can be offered by simple discrete protectors. Maxim offers several algorithms for fuel gauging. On the left, we are showing the simple voltage-based algorithm called ModelGauge. This patented algorithm overcomes the problems explained earlier about voltage-based fuel gauging by using a very innovative scheme that we will review in more detail shortly. In the middle, we are showing an algorithm called ModelGauge M3 that provides excellent accuracy by combining Coulomb counting with ModelGauge. This combines the benefits of Coulomb counters, such as very good short-term accuracy, with the benefits of ModelGauge, such as excellent long-term stability. On the right, we are showing an algorithm called ModelGauge M5 that adds robustness and enhanced accuracy to ModelGauge M3. This algorithm also enables EZ configuration that eliminates the traditional requirement of characterizing batteries over various loads and temperatures in order to provide accurate results. This algorithm also has some advanced features like dynamic power, with which a host system can extend the runtime by adjusting peak and sustained load as per guidance from the fuel gauge. Some implementations also offer cycle plus age forecast that essentially informs the system about how many equivalent battery cycles are forecasted to be available as the battery ages. The customer can make use of this information to plan timely battery replacement or adjust charger parameters to extend the battery life. All of the algorithms are available in host-side fuel gauge implementations, while ModelGauge M5 is available for pack-side implementation. Maxim also offers these algorithms in power management ICs with integrated chargers. Now let's look at how voltage-based ModelGauge works in lithium-ion batteries. The plots show the relationship between state of charge, SOC, and open circuit voltage, OCV, which is essentially the relaxed cell voltage when there is no load on the battery for a long time. You will notice that the curve for an old battery overlaps that of a new battery, even if the absolute capacity of the old battery is much smaller than when it was new. Of course, this curve is slightly different for a lithium-ion battery of different chemistry. Using these curves, if we are able to find out the OCV of the battery, we can translate that to SOC. ModelGauge essentially estimates the OCV at all times, even when the battery is under load. It estimates the OCV, shown in yellow, by measuring the immediate voltage and by running a real-time simulation of the battery model using battery characterization and past voltage history. Once it estimates OCV, then it is able to translate that to SOC based on the curves that we saw earlier. Now let's look at an alternate method of fuel gauging typically used by competitors who use a Coulomb counter. The light purple line shows the ideal state of charge. The dark purple line shows the error caused by the offset accumulation drift. This error cannot be corrected as soon as the load goes away. The IC must wait until the battery is fully relaxed. This can take anywhere from half an hour to more than an hour, depending on the battery chemistry and temperature. Once the battery relaxes, the IC makes a voltage measurement and treats it as OCV. Ideally, the state of charge would be corrected to match the light purple line. In reality, the battery may not be fully relaxed, or there may be a cell-to-model mismatch causing an overshoot or undershoot. Now the fuel gauge is stuck with that error until the next relax event happens. This correction mechanism is fraught with problems, as in many modern applications, the load may never truly go away for long periods of time due to a radio pinging from time to time, and the occasions for the battery to relax may happen very infrequently, a few times per day at the most. So the Coulomb counter continues to accumulate error continuously until these correction events take place. All these errors then need to be corrected all at once, resulting in a jump in the state of charge. Even if the competitor is able to hide this jump by smearing the result over time, there is an inherent error nevertheless. Now let's look at how ModelGauge M3 and M5 work. Even Maxim ICs have some offset error in the current measurement that causes a small drift. However, since the IC has an estimate of OCV from ModelGauge running in parallel to the Coulomb counter, it is able to immediately steer the SOC result back on track. This happens continuously, regardless of whether there is load on the battery or not, thrice per second, and more than 200,000 times per day. So the errors that need to be micro-corrected are very tiny and are invisible to the customer. This is a huge advantage that ModelGauge M3 and M5 have over the competition. This illustrates how ModelGauge M3 and M5 use ModelGauge to micro-correct the Coulomb counter continuously. The red lines show that in the short term, the Coulomb counter has a very small error, but it drifts in the positive or negative direction continuously, resulting in a large error over time. In contrast, ModelGauge, shown by the blue line, has short-term errors but is very stable over the long term. When the two are combined, the resulting error stays within the green lines in a bounded manner even over the long term. So how do you choose the right fuel gauge technology for your application? If ease of use is the key criteria, choose ModelGauge M5EZ. Of course, for high-volume applications, Maxim can provide customer characterization. If accuracy is of key importance, then choose ModelGauge M3 or M5. This is important especially if the empty voltage is high, or if the load is high. C/4 means if the battery has 1,000 mAh capacity and the load is 250 milliamps. If the load is 300 milliamps, this is higher than C/4. The plot on the right explains a safe area, where ModelGauge will provide good accuracy for light loads and low empty voltage. But outside of that, ModelGauge M3 and M5 are highly recommended. If very low quiescent current is critical, choose ModelGauge that will run at an industry-low 3 microamps. Even ModelGauge M5 at 7 microamps is very low too, considering that it is a hybrid approach that uses Coulomb counting. If the decision is size or cost driven, choose ModelGauge. For special features like time to empty or time to full, choose ModelGauge M5, Max 17055. For other special features beyond Max 17055, such as non-volatile memory, pack-side application, multi-cell, authentication, or cycle plus age forecast, choose the ModelGauge M5 Max 17200 family. Now let's look at how ModelGauge M5 stacks up against the competition. To make a fair comparison, we tested a fuel gauge with a built-in custom-tuned battery model inside an iPhone battery pack over a variety of loads and temperatures. You can see that the ModelGauge M5 errors in teal are far lower than the competition in red. One of the main benefits of a fuel gauge is that the system designer can use it to decide when to shut down the device in case of a low battery condition. If the fuel gauge overestimates the battery state, this planned shutdown threshold may never be reached before the battery voltage falls below the minimum operating point of the device, resulting in an unexpected crash that can corrupt data or cause some other harm to the system. Fearing this, if the designer shuts down the system prematurely, then the runtime becomes shorter, and that is highly undesirable from a user experience perspective. By offering excellent accuracy, ModelGauge M5 allows the designer to trust the fuel gauge and plan for a graceful shutdown while still maximizing runtime. This histogram, showing number of test scenarios over various operating conditions of load and temperature versus state of charge error buckets, illustrates that ModelGauge M5 delivers very high accuracy with no more than 1% error in the majority of test cases, while the competition shows much higher error near battery empty conditions, where the need for the fuel gauge accuracy is the most critical. Many new devices such as wearables and small IoT devices use very small batteries in order to reduce size and weight. Long-term studies show that these devices spend a significant portion of time in a standby state. So it is critical for the system components to stay in a very low power mode during that time as well. Otherwise, they will use up a significant portion of the battery capacity and reduce the runtime for the active state of the device. ModelGauge Max 17048 runs at lowest in class 3 microamps, while ModelGauge M5 Max 17055 or Max 17201 provide a solution by running at the lowest in class 7 microamps, while still providing fuel gauge updates regularly. Maxim fuel gauges have no lower limit as to how small the batteries are, unlike the competition. One of the big challenges for fuel gauges is that traditionally, they have required extensive characterization and analysis of each battery for specific application conditions for getting the best state of charge accuracy. This means that the customer has to perform complicated characterization on their own, or ship the battery to the fuel gauge vendor. With new transport safety regulations, this has become a complicated logistics effort. Once the battery arrives, the fuel gauge vendor can take 2 to 3 weeks for running the tests and analyzing the results. This time and effort make it difficult to support fast-track projects or projects with uncertain volumes. The Max 17055 and Max 17200 family provide a solution by supporting ModelGauge M5EZ. That eliminates battery characterization. The system designer can use the EV-Kit software to step through the application details and generate the model in just a few minutes. Maxim has run simulations using more than 300 different batteries and 3,000 discharges, and summarized the results in the form of a histogram that shows that this method results in less than 3% error in more than 97% of test cases. Competition has claimed to offer generic battery solutions, but have not demonstrated how well they work across various batteries and operating conditions. New high-performance processors ramp up quickly and cause the battery voltage to drop drastically. This is okay when the battery is full, but as the battery starts getting discharged, the battery voltage can approach a very low level and cause an unexpected crash. ModelGauge M5 Max 17055 and Max 17200 family provide a solution for this challenge by incorporating the new dynamic power technology. The processor informs the fuel gauge the minimum battery voltage the system can tolerate without crashing. In turn, these ICs recalculate the maximum pulses as well as sustained load the system can draw, and still keep the battery voltage above the minimum threshold. The processor uses this information to throttle appropriately and gets the best performance for the battery state at that time, and dynamically adjusts the throttling as the battery gets discharged further by repeatedly checking in with the fuel gauge. There is a new trend in devices to provide faster charging. Due to safety concerns, designers want to monitor the battery very carefully as they are pushing very high currents while fast charging. For some customers, preventing unauthorized clone batteries is an important requirement to prevent potentially unsafe batteries from being used with their systems. Max 17055 offers a solution by accurately monitoring the voltage, current, and temperature when embedded in the battery pack. This eliminates the sensing errors due to voltage drop in the battery connectors. Max 17055 can store the initial battery model to make the driver simple. The IC also contains a unique ID that enables cloud-based authentication in combination with another host-based unique ID. In addition to a 64-bit unique ID, the Max 17200 family provides industry-leading SHA-256 authentication with a 160-bit secret key. This is important to prevent unauthorized aftermarket replacement of the battery, which can be dangerous due to high charge currents that can damage a poorly designed battery. Here is a comparison chart of various fuel gauges that we offer for single-cell applications. We will highlight a few key parts. Let's start with ModelGauge Max 17048, which only uses voltage while still providing accurate fuel gauging. This is the simplest, smallest fuel gauge in the industry, while also working at the lowest quiescent current in the industry of just 3 microamps. Now let's look at ModelGauge M3 Max 17050, which combines Coulomb counting and ModelGauge. Coulomb counting provides excellent short-term accuracy, while ModelGauge provides excellent long-term stability. Next, let's look at ModelGauge M5 Max 17055 that refines the hybrid algorithm further to improve accuracy and robustness, enabling the EZ configuration that eliminates battery characterization. This IC is ideal for host-side applications, while pushing further on lowering the IQ and integrating the temperature sensor compared to MAX 17050. MAX 17055 is pin compatible with the MAX 17050. This IC also supports new features such as dynamic power and new chemistries such as lithium ferrous phosphate. Then finally, let's look at ModelGauge M5 MAX 17201 or MAX 17211. These ICs integrate non-volatile memory and SHA-256 authentication for pack-side applications. These ICs are also the smallest and run at lowest in-class IQ for pack-side applications. This is a comparison of various multi-cell fuel gauges that we offer. On the left, we show ModelGauge MAX 17049, which only uses voltage while still providing accurate fuel gauging. This is the simplest, smallest, multi-cell fuel gauge in the industry, while also working at the lowest IQ in the industry. Finally, let's see ModelGauge M5 MAX 17205 or MAX 17215 that can be used for 2 and 3 series cell applications with cell balancing, and even beyond that to any number of cells by monitoring the cell stack. In this session, we learned that fuel gauging lithium-ion batteries is difficult, but critical to good user experience. We looked at various fuel gauge techniques and ways to implement the fuel gauging function. We saw how Maxim has the best portfolio of fuel gauges to serve all kinds of applications. The key benefits that Maxim fuel gauges offer are excellent accuracy, easy to design in, very small size, lowest in-class IQ, host side and pack side options to suit every application.
For more information on this topic, please go to our website at www.maximintegrated.com under Products, Power, and Battery Management. We hope you enjoyed this video and see you again in another educational video of Maxim Integrated.